and the next speaker, according to our initial schedule, I guess, yeah, Dr. Huan Doan, who is here. Yep, hello. So, University of Bristol, UK, Department of Mechanical Engineering, and the topic is novel hierarchical copper-based metal organic frameworks for improved catalytic performance. So please, Dr. Huan Doan, the microphone is yours.
Right, so first of all, I would like to thank the organizer for giving me a chance to present my work in this conference. My name is Huan. I'm currently a postdoc at the University of Bristol. The work that I'm going to present today is about novel hierarchical materials for improved catalytic performance. Just a little bit about myself. So I'm always very excited about my PhD and my life in academia in the way that I have had chance to attend a lot of conferences and present in front of many audience. Sometimes attending conference also means that I have a chance to travel to many beautiful cities, engage with friends and colleagues, and enjoy food, take part in some entertainment activities. However, it seemed not to be this case during the COVID-19 when every conference was cancelled or turned into being virtual. It's still good in the sense that now I can attend the conference without paying a lot of money for registration fee, flights, and accommodation. The topic that I'm going to present today is about metal organic frameworks or MOFs, which are a new type of porous materials constructed from metal nodes and organic linkers. To name a few of commonly studied MOFs, they can be ACAS1, also called copper BTC, UIO66, MOF 74, and ZIP8. These MOFs have been extensively studied in catalysis, gas separation, energy storage, and drug delivery. For many years, many research have been carried out to discover new MOFs with robust framework structure and high surface areas by changing ligand and metal side functionalities. Recently, there have been an emerging studies done by many people to change pore structures and morphology in MOFs. The modified MOF normally have increased molecular diffusion and accessibility and have a greater performance in catalysis. These emerging technologies has defined a new type of pore regime in MOFs called hierarchical pore structures, where a mesopore or macropore by somehow can be introduced into a microporous MOF. I have added some quick video here to show why the pores are matter. So this is the structure of the porous materials. So in most of the porous materials, the reaction will be performed in the pores where the reactant can contact with the active site and be broken into small species. Yeah, I think it's a bit loud. Yeah, just want to say that, yeah, this species will be contact with the active site and broken into small species before the final products will form. However, for microporous materials, some reactions are really limited because big molecules cannot travel into the pores. And that's why I'm interested in designing new macroporous MOFs to improve the diffusion accessibility of the reagent to the sample in catalysis. Macropores MOF can be synthesized by different methods. Some of the commonly used methods are structural templating, acid etching, and the use of CO2. In the first method, MOF was formed around a macropore template to obtain composite materials. In this method, it's very difficult to remove the template after the synthesis without the collapse of the pore structures. And macropore MOF can also be synthesized by acid etching methods. These methods normally results in effect formation and be performed without a complicated synthetic process. However, we need to be very careful because some MOFs are very unstable in acidic condition. The method that I'm going to introduce today is the use of supercritical CO2, where the MOF precursor solution was pressurized with CO2 in a critical condition, like 40 degrees C and above 71 bar. And this method has been claimed to be to have many advantages for the synthesis of hierarchical MOFs. In most of the conventional MOF synthesis, for example, the hydrothermal synthesis of ECAS1 carbon node and trimesic acids are mixed in DMSO to make a stop solution. After that, a copious amount of methanol need to be added and heat at 40 degrees C and left for a few days. After that, the solid MOF will be filtered and rapidly washed with methanol to remove the solvent in the pores. Using supercritical CO2 methods, we have found that we don't need that much solvents, which is good for scale up the synthesis without using the big volume reactors. And the solid ECAS after filter and dry can be used straight away without washing as required in the hydrothermal synthesis. These methods can help to produce MOF in a continuous system. Also minimize the risk of pore collapse during the washing step, which have been reported as a main issue in some MOF synthesis. We also found some interesting results of MOF synthesized by these methods. First, we can see that the supercritical CO2 can introduce a rapid nucleation after a few minutes. This is much faster than 12 or 20 hours in reported synthetic methods. Also, increasing CO2 pressure can help to increase the average particle size. This suggests the more rapid nucleation at higher pressure, which is similar to when we add a large amount of solvents. And these results demonstrate that the particle size and dispersivity can easily be controlled by varying the CO2 pressure. The SCM image show that the sample synthesized in longer CO2 exposure times after 24 hours have a lot of macropores without compromising the highly micropore structures. The level of macroporosities can be asserted by the appropriate choice of CO2 pressure. These results demonstrate that by tuning CO2 pressure and time, we can change the MOF properties such as particle size, morphology, and porosity to obtain design materials for catalysis, which we have no chance to do in the normal hydrothermal synthesis. To prove the benefit of introducing macropores in catalysis, we took the sample synthesized in CO2 at the 75 bar and 72 hour to compare with the normal ECAS with only micropore structures. The gas absorption results show that the surface areas of CO2 is lower than the normal ECAS, which is due to the defect in the CO2 sample. And normally, the lower surface areas will compromise the catalytic activities, but we will see how these materials perform in the later slides. We also notice that the micropore structures of these materials are similar, which is confirmed by the similar pattern of the nitrogen isotherm at low pressures. And yeah, and this is also confirmed by the similarities in the XRD results of these two samples. We also notice that both samples start to decompose at around 280 degrees C, and the lower thermal stability in F-gas CO2 might due to the smaller particle size of this sample compared to the normal F-gas. And copper is an active site in F-gas MOF, so we test the elemental composition of these materials and notice that the F-gas CO2 have slightly lower copper content than the normal F-gas, which might due to the defect formation in the CO2 sample. And first, we test this sample in gas phase reaction. And here we use CO2 oxidation reaction as an example because the copper side in F-gas, the MOF that I'm working on have shown some activity in this reaction. Before the reaction, both sample was activated in a flow of CO to remove the coordinate with the molecules on the copper side in the MOF. After CO activation, both samples show an increase in the low valence copper contents, confirming the reaction of CO during the experiment. And the new carbon oxygen bond containing species in the carbon signals for F-gas CO2 confirm the defect which was revealed previously in this sample. However, it's still can see that the majority of the carboxylic species remain intact, allowing us to make a fair comparison in the catalytic performance in this sample. In the gas phase reaction, both samples start to show CO oxidation activities once the temperatures reach at 220 degrees C, and the rate of CO oxidation increase rapidly with increased temperatures. It can be seen that the CO2 maintain higher activity than the normal F-gas at all temperatures. For example, at 240 degrees C, after 60 minutes, the composition of COs over F-gas CO2 was increased from a baseline of around 13% for normal F-gas to about 30%. Demonstrate that the CO molecules could access to the open copper side in F-gas CO2 more efficiently than in normal F-gas at these temperatures. And note that the F-gas CO2 sample has decreased surface area and sorry, I just said and have a slightly lower amount of copper than the normal F-gas, which could normally have compromised the activities. So the increased catalytic activity of the F-gas CO2 attribute to the existence of the macropores in the F-gas CO2, which was seen previously in the SCMs. The positive effect of introducing macroporosities to F-gas 1 on the catalytic activities are expected to be greater in the case where the diffusional barriers are greater. Therefore, we compare the performance of the hierarchical F-gas materials in a model liquid phase reaction involve larger molecules to determine if this is indeed the case. So before the reaction, we encapsulate both samples with phosphomolytic acid hydrate. We call that is HPMOs, which has an efficient prostate size and a relatively small cluster size for this kind of reaction. So these two samples with comparable molybdenum contents have activities in the metabolysis of styrene oxide compared to no activity in a blind sample and the sample without encapsulation. So here we focus on initial rate enhancements and believe this reflects the true kinetics performance of the catalyst. Comparing the encapsulated HPMO samples, so after 10 minutes reaction, about 70% styrene oxide react using ACAS CO2 compared to about 3% in normal ACAS. So note that the reaction rate of the styrene oxide metabolysis over these two samples were normalized by the molybdenum loadings. This result show that the HPMO loaded ACAS CO2 has better reaction kinetics than the HPMO loaded normal ACAS, which might be due to more accessible macropore structures in these materials. So we also have demonstrated that the macropore structures in ACAS MOF produce a greater improvement in catalytic performance of liquid phase reaction when compared to the gas phase reaction. This results evidence that the macropores may be beneficial in overcoming the diffusional limitation, which are more prevalent in liquid phase reaction than in the gas phase, and have a greater effect on reaction where bunking molecules are involved. To conclude, the supercritical CO2 can be used to trickle the MOF reaction with a great reduced amount of solvents. And we see that using CO2, macropores can be introduced in the MOF, and the size of the pore can be controlled by adjusting CO2 pressure and times, and the increased catalytic activities in the MOF is really caused by the existence of the macropore in the sample, and introducing macroporosities in MOF are expected to be greater in case where more bunking molecules are involved. I would like to thank all my supervisor at the University of Bristol and University of Bath, the sponsor and the collaboration I have during my PhD, who have helped me to gain a success in this school. And lastly, thank you for your attention.
So thank you, Huan Doan, for interesting presentation. Okay, so do we have some questions to the speaker? Let's check. Colleagues, please. No. Don't be so shy. Okay. Probably people still thinking about the questions. I have one. So you can vary the size of these pores, yeah?
Yeah.
By some triggers. And what is the range of these pores you can construct? I mean, what is the minimum maximum size of the pores? And
yeah, so for using the supercritical CO2, I vary the pressure between 0 bar to 90 bar, and the maximum pore size that I can obtain is about 300 nanometers.
300 nanometers.
Yeah.
Okay.
Well, this really depend on the time as well. So because I noticed that when we leave it in longer CO2 exposure time, the crystal size will be also increased, and also when we change the pressure, it's also change the pores. Yeah, but for the short answer, it's around 300 millimeters.
Okay, thank you. Now it's quite hot topic. I mean, these metal oxide frameworks for different functional, for different applications. So I don't know if we don't have any questions. Let's thanks PK again. Thank you, Huan Doan.
Yeah, thank you.